Section 2.3 is going to introduce what are not called basic derivative rules. So we're going to have 3 derivative rules, 2 of them in this section and 1 of them in section 2.4 that are not basic ones. Okay, they're more complicated, they're messier. And the first one we're encountering today is called the product rule. So when we did sum and difference rules, we found out we can take the derivative of each of them individually, and then we can add or subtract them back together, right? So the first question that you might want to ask or think might be true is, can you do the same thing with products? We could do it with limits. You take the limit of this little piece, you take the limit of this little piece, and you multiply them. Can we do it with derivatives? So we're going to do an example to explore whether or not that actually works. So the example we're going to do is having the function 4x to the 9th for f, and for g of x is the function x cubed. So this first one here where it says then f of x times g of x, and then prime says, working inside out, the first thing I'm going to do is I'm going to multiply 4x to the 9th times x cubed. And after I multiply them, I'm going to take the derivative. So what is 4x to the 9th times x cubed? Be bold. Somebody tell me. What is it? 4x to the, what was it? 12. Yeah, 4x to the 12. Okay, everybody good with that? Just multiply the 2 values together. And then we're going to take the derivative of that. So what is the derivative of 4x to the 12th? Yep, 48x to the 11th. Okay? That really, really, really is the derivative of this problem. Okay? So what we're trying to decide is, could I have taken the individual pieces' derivatives and still got the same answer? So we're going to try it. We're going to take the derivative of 4x to the 9th, and we're going to take the derivative of x cubed separately. So what's the derivative of 4x to the 9th? 36x to the 8th. And what's the derivative of x cubed? 3x squared. And what happens when I multiply 36x to the 8th times 3x squared? What's 36 times 3? With a calculator if you want to, I don't care. 108. And what is x to the 8th times x squared? Yeah, x to the 10th. And lo and behold, good grief. These two are not equal. They're not. I can't just take the derivative of each piece individually and then multiply them. I wish I could. It would make all of this so much easier if it worked, but it doesn't. So, what do we do instead? Well, we don't do that. Okay, here's what we do. So when we're trying to take the derivative of it, where I actually can't multiply the insides together first, like I just did on that last problem, I need to be able to do something different to work through this. What I do is I take the derivative of the first piece, and I multiply it by the second piece. Oh, I said it backwards if I have written up there. I take the original of the first piece, and I multiply it by the derivative of the second piece. And then I add it to the reverse. I take a derivative of the first piece and multiply it by the second. And if you switch the order of the addition, of course, it's the same thing, so it doesn't matter the order of that. So since I showed you something on the last slide that absolutely didn't work, I'd like to show you that this works for that example. So if I take 4x to the 9th and x cubed. Well, this says I rewrite the 4x to the 9th. And then I do the derivative of x cubed, which we said before was 3x squared. Then I take the derivative of 4x to the 9th, which was 36x to the 8th. And I write the original of the gx cubed, or gx, which was x cubed, like so. That's what this says to do. Derivatives of each piece individually multiplied by the original of the other one. And then we're going to multiply and clean things up. Well, 4 times 3 is 12. X to the 9th times x squared is x to the 11th. The other piece, I have 36 times 1, so it's 36. X to the 8th and x cubed is x to the 11th. And what is 12 plus 36? 48. X to the 11th. That's exactly what I got when I multiplied the values together first on the inside. Right? So it really did work, whereas the other way I tried it didn't. I'm not going to ask you to replicate this process to show why this process works. That's not my point. But I do want you to be convinced that it does work. All right? It's not just some hocus pocus I'm throwing out there and expecting you to accept. Now, some problems, like number 1 here, you could do the algebra and multiply it out and then do the derivative. Agreed? And that might actually be preferable for this problem. It might actually be nicer and cleaner to do. We're practicing this process, so it doesn't really matter which one's nicer or cleaner. I'm just wanting us to practice it. The second problem, however, that you see on your sheet, this one, there's no way to simplify x cubed and cosine x any more than it's already simplified on here, right? There's nothing I can do. So I don't have the option of doing algebra or trig in this case to simplify something before I take derivatives. It's not even a possibility. So let's go back to the first one. We're going to practice this process. My individual pieces are now underlined. And we're going to take the derivative of g of x. So what I suggest doing, because I like that I can always start it, is to just rewrite the first piece. X cubed plus 3. And then to take the derivative of the second piece. So what's the derivative of x squared minus 5? 2x, that's right. And then it's addition. And now I go back to the first piece and I take its derivative. Oh, I typoed it. Thank you. Thanks, Faith. Okay. Better. X squared plus 3, and then I have my 2x. All right. What's the derivative of the x squared plus 3? It happens to be 2x again. And then I write the original of the second piece, x squared minus 5. Now, Gateway, next Thursday, you stop right there. You don't do anything else. You guys are like, man, you're psyching me out for this whole Gateway thing. Absolutely love that I don't have to simplify it all. No, not. Yeah, simplifying is no good, right? I mean, it's not no good. It introduces the possibility of making another error. So you can stop right here on the Gateway. As you're working through homework and tests and all that jazz, we're going to clean it up. So we're going to simplify what we can. And on this one, that's kind of all of it. I can actually distribute the 2x. So now I have 2x cubed plus 6x. And I can distribute the 2x over here, giving me 2x cubed again, and minus 10x. My net result is 4x cubed minus 4x. Any questions? Does that make sense? Cleaned it up. So on this one, like I mentioned, we actually have to use the product rule. Over here, if you encountered this problem on, on a quiz or on a test, you would be able to have freedom to choose how you wanted to do it. Do you want to multiply it out and then take the derivative, or do you want to take the derivatives and then multiply them out? You would be able to choose that. Over on this one, there are no choices because there's nothing you can clean up between x cubed and cosine x to represent it in a different way. So you're sort of forced on this one to use the product rule, whether you wanted to or not. So the first piece is rewritten, x cubed. What's the derivative of cosine of x? Negative sine of x. And then I need the derivative of x cubed, which is 3x squared. And then I rewrite cosine of x. Now the cool thing on this one, and it's not always true with trig and so forth, but a lot of times it will be, especially when you're combining a trig piece with a polynomial piece like this one is. There's really not a lot you can simplify. There isn't. The only thing that I'm going to do is I'm going to pull that negative in front of the sign out to the beginning. So this I'm going to rewrite it as negative x cubed sine x plus 3x squared cosine x. That's it. And lo and behold, I'm done. So that's quite friendly. Product rule is not the only rule in this section. We also have the quotient rule. Products and quotients kind of go hand in hand, so that's why they're put together in the same section of material. And we're going to do the same thing we did when we started with product rule. Man, it would be really nice if I could just take the derivative of the top, the derivative of the bottom, and then make that happen. It would be really nice. So we're going to use that same 4x to the 9th and x cubed that we did before and explore that possibility. So if I did 4x to the 9th over x cubed, I can actually simplify 4x to the 9th over x cubed. What would it be? For what? Yep, x to the 6th, you got it. And then the derivative of 4x to the 6th would be 24. We're going to multiply, so not add. 24, and then x to what? The 5th, right. Okay, this is really the answer because I did it sort of order of operations. Worked on the inside because I was able to, moved to the outside, took the derivative, and I'm done. Okay, so what we're trying to see is if it would work if I just did the individual derivatives first and then division second. So, oops. What is the derivative of 4x to the 9th? We already did this, so what is it? 36x to the 8th. And the derivative of x cubed, we've seen a couple of times, to be 3x squared. 36 divided by 3 is 12. X to the 8th divided by x squared is x to the 6th. And again, no, it doesn't work. I can't do the individual pieces and then just mush them back together in a division problem. So what can I do? Well, the quotient rule. The quotient rule on the top looks much like the product rule, but with subtraction. Much like the product rule. And then in the denominator, it becomes the denominator squared. So I have g of x, f prime of x, minus f of x, g prime of x, over g of x squared. And let me introduce, after you write it down, a couple of maybe helpful reminders about how to remember where all the pieces come from and where they go. So one of the ways you can think about this is that we're taking the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so that's something you could say, right? Think about it in that fashion. When I was in high school, I took a calculus class, and I took calculus classes in college as well, but the mnemonic device that my teacher did in high school looked like this. High is what's on top. Ho, sometimes I'll have people tell me that their teacher did low is what's on bottom. But let me show you what happens if you use the high and the ho. Okay? So this is what she did. She said ho, the bottom, times the derivative of the top, d high, minus high times the derivative of the bottom, which is d ho, all over ho ho. And that's how I remembered and learned the quotient rule. And I think part of the reason why it stuck with me is Heidi Ho comes from a television show. Does anybody know what television show it comes from? Has anybody ever seen Home Improvement? Old television show. You can buy it on Netflix. We actually did. My kids think it's hilarious. Home Improvement is a television show, and the neighbor, his name's Wilson, talks to Tim the Toolman Taylor across the fence, and he says, "Heidi ho." Heidi ho, that's what it is. So that was one of the things for me that was helpful in remembering. Of course, you've got Santa Claus on bottom. I mean, who can't remember that, right? Ho ho, right? All right, let's check to see that it actually works for the problem that we had. So our problem was 4x to the 9th over x cubed. It says we're going to do the denominator, x cubed, times the derivative of the numerator, which was 36x to the 8th. Hang on, left out my 6. Minus the numerator, which is 4x to the 9th, times the derivative of the denominator, which is 3x squared, over the denominator, x cubed squared. So again, if this works, if this is correct, I should get 24x to the 5th. That's the real answer here, 24x to the 5th. Was it 5th? Yeah, 5th. Okay, so let's take a look. Well, at the beginning, I have 36. X cubed and x to the 8th is x to the 11th. Minus 4 times 3 is 12. And then x to the 9th and x to the 2nd is x to the 11th. And what is x cubed squared? X to the 6th. What's 36x to the 11th minus 12x to the 11th? It's 24. X to the 11th. And then x to the 11th over x to the 6th is x to the 5th. Exactly what it should have turned out to be if I had simplified first with order of operations. So it works. It's true, and it is correct. This is our quotient rule. All right, so quotient rule, we're going to do some examples. Of course, the reason I chose those 4x to the 9th and x cubed was because I was able to combine them, right? I wanted to show that it really worked for something that I could have used a different method to do it for. But just like with the cosine problem that I had earlier on problem number 2, you can't always actually do simplification first, which is why we have a need for the quotient rule, right? When the simplification first is not a possibility. And this is a very good example of this. Now, this looks quite different. I mean, let me take a step back. There's ways in which this looks similar to a problem I did in the last section. Do you remember the problem where I separated it and became 3 separate fractions? Yeah? Okay. The reason I was able to do that is because the denominator didn't have addition or subtraction in it. Are you with me? When I have the addition and subtraction in the denominator, if I tried to separate these, I would have t squared, but the t squared would be over 5t minus 3. And I would have 4, but it would be 4 over 5t minus 3. And I'd still have addition and subtraction in the denominator, which is causing me problems because I can't reduce anything still. Okay? So that addition and subtraction in the denominator is another place where I'm forced to use the quotient rule instead of having the ability to do some sort of a simplification with fractions. So, with the quotient rule, it says I'm going to do the denominator, 5t minus 3, times the derivative of the numerator. So what's the derivative of t squared plus 4? 2t, yes, thank you. Subtraction, all right, subtraction. And then I need the numerator, t squared minus 4. Plus 4, times the derivative of the denominator. What's the derivative of 5t minus 3? Just 5. All right, so let me pause here and talk about 2 common mistakes. Common mistake number 1 is using addition instead of subtraction. Okay? Quotient rules, subtraction, product rules, addition. So you've got to keep that straight. The other really common mistake here is flipping the order of the subtraction. So in other words, that t squared plus 4 times 5 being at the beginning and the other part being at the end. So you always begin the quotient rule with the denominator. Always beginning with the denominator, and then everything falls into place after that. All of this needs to be over the denominator, 5t minus 3 squared. Derivative gateway, you stop right there. Won't that be fun? Yeah, but it's even more fun right now because we get to simplify it. So we're going to distribute and clean things up. So my 2t would be multiplied through, so I have 10t squared minus 6t. And my 5 will be distributed through. And there's a negative here, so be careful about that. So it's really like distributing through a negative 5. I have negative 5t squared and negative 20. Avoid the temptation to square the denominator. That will never lead to anything productive. You may leave the denominator always in squared form. Okay? Don't go simplifying what's not necessary. And we'll clean up the numerator where we can. And we can in a couple places. So I have 10t squared minus 5t squared, so that's 5t squared. Minus 6t and minus 20. All right, let me talk about that numerator for a sec. The reality is we should check to make sure that nothing in the numerator simplifies the denominator. In other words, that I don't have a 5t minus 3 somehow in the numerator. Does that make sense? Now, if I tried to factor the numerator, I would in fact have a 5t on one of the pieces and not on the other one. Agreed? That's what would happen in the numerator. But there's absolutely no way to put a 3 right here. Why not? Think about what you know about factoring. Why is there never going to be a 3 right there in this particular problem? Yeah, tell me, Michaela, what you mean by that. You're right.
Because you multiplied the negative 20 whenever you use your factoring.
Yeah, those two spots right there have to become 20 when you multiply them. I can't take 3 and multiply it by something and get 20, right? Not whole numbers. It's not possible. So there is no way to factor this and actually get it to cancel with the 5t minus 3 in the denominator. It might factor into something, but unless it cancels with the denominator, it doesn't really matter. So, because I visually can check that, I know I'm finished with the derivative. And then we stop there. All right, let's take a look at another one. This one involving trig. So we've got h prime of x. What comes first? The denominator, x cubed. And then what's the derivative of the top? Cosine. Derivative of sine is cosine. And then it's subtraction. And now we flip the order. I've got my numerator. And I have the derivative of the denominator. So what's the derivative of x cubed? 3x squared. And all of this is over the denominator, x cubed squared. Now, remember over here that I said we clean things up, but in particular we're trying to look and see if the denominator somehow reduces with something on top. This denominator will, because I have an x cubed here, an x squared here, and an x cubed here. I'm definitely going to be able to get rid of some of those x's because there's an x multiplication factor in every single term. So before I worry too much about how they're going to cancel, let me clean things up a touch by just listing the values first. So I have x cubed cosine of x minus, I'm going to write 3x squared just to being the front of it, and then over sine of x. And then what's the denominator? X to the 6th. Good. How many x's are allowed to reduce or to cancel out? 2. There's an x squared here. I have an x cubed here, which means there's an x squared in it, right? And I have an x to the 6th here, which means there's an x squared in it. So I'm going to reduce each of them by a power of 2, right? An x squared value. So x cubed reduced by x squared becomes x. I still have my cosine of x. I still have the negative 3 that comes after that. The x squared here itself completely cancels, right? X squared divided by x squared is 1. So I have just the sine x here. And what will the x to the 6th in the denominator become? X to the 4th. So this is what I end up with as the reduced or simplified form of this denominator, of this fraction. Okay, so product rule, quotient rule. The other thing that's showing up in this section is going to be the derivative of all our other trig functions, okay? Sines and cosines, I find those to be very easy to remember. That's me personally. The next ones are not quite as easy to remember. You need to know them for your gateway, so you've got about a week to make sure you can get those memorized and get them down. But this is what we have. Tangent, cotangent, secant, and cosecant. So the derivative of tangent is actually secant squared. Make sure you write x next to it. Otherwise, it's like saying square root, and you're like, well, square root of what? Has no meaning without the x next to it. The derivative of cotangent of x is negative cosecant squared of x. So these sort of feel like they go together, right? Tangent to secant, cotangent to cosecant. The derivative of secant of x is secant x tangent x. And the derivative of cosecant of x is cosecant of x, cotangent of x, and there's a negative at the beginning of that one. Now, there is something kind of cool that happens. Take a look at all the co-functions here, and I'll write the other two that we have on our screen too. So if I have sine x, its derivative is cosine of x. And if I have cosine of x, its derivative is negative sine of x. These are my three co-functions, right? All of their derivatives are what? Negative. That's kind of helpful to remembering these. If I take the derivative of a co-function, I'm going to get a negative involved. And if I'm not taking the derivative of a co-function, there's not a negative involved. And then it's nice also to remember them sort of in pairs. These two seem very similar, right? Tangent to secant, cotangent to cosecant. And these two again have that same similar, that similar form to them. Secant to secant tangent, cosecant to cosecant cotangent. So we're going to try some with these. Okay, does everybody have them? Cool. All right, so the first one, recognize that you might have to rewrite. How do I rewrite 1 over x? X to the negative 1. So I'm just going to jot that down sort of above here. I'm not going to write a separate step. What's the derivative of x to the negative 1? Negative x to the negative 2, right? Decrease the exponent by 1. All right, what is the derivative of secant? Secant x tangent x. And the negative 12 at the beginning is simply a constant multiplier, so it comes along for the ride. So the negative 12 is there. The derivative of secant is secant x tangent x. And then the only cleanup I have to do is the polynomial piece right here at the beginning. I don't have any negative exponents to start the problem, so I should have no negative exponents to end the problem. So how would I rewrite negative x to the negative 2? Yep, and it's negative, so put a negative either out in front or on the top. And then the other piece is negative 12 secant x, tangent x. Okay? Number 6 is actually a question I've used on tests before, and students screw it up every single time. Lots of students. Okay, sine of x times cosine of x. What overarching rule do I need to apply here? It's product rule. That's what people forget. think when trig functions are multiplied, sometimes we forget where the multiplication is occurring or that it is occurring. This is a product rule, so you have to use the product rule. Yeah, I need to know the derivative of sine's cosine, the derivative of cosine's negative sine, but I got to do it with the product rule. So with the product rule, the first thing I do is simply rewrite the first piece, sine x. What's the derivative of cosine? Negative sine of x. And then product rule has addition. And then I'm going to do it in the other order. So what's the derivative now of the sine of x? Cosine of x. And I rewrite the second piece, which is already cosine of x. And in terms of calculus, I'm really done. Now, there's a couple of cleaning up things that I can do in terms of visuals, right? Like the negative can come to the beginning. What's another way I can write sine of x times sine of x? I can write sine squared of x, and the squared goes right here. And you can do the same thing for cosine squared of x on the second piece. The reason we want to make sure that the squared goes by the sine or by the cosine is because we don't want to think it's x that's being squared. It's really the sine of x that's being squared. So that's why we put it next to the sine or the cosine. And you're done. It's not so bad, right? You do have to recognize it, but it's not so bad. All right, we will pause there for today. I have 2 more examples. What I'm going to do is I'm going to go ahead and record the next 2 examples and post them for you because I don't want to get behind and then end up having to try to rush before a test. So stay tuned. There will be a second part to this video that I will post. I will post it at the same time I post this one. You'll need to watch the second part of the video, literally probably 7 minutes. That's it, okay? And then after you watch that, you'll have the ability to do all the homework that goes with this section too.